I will begin with a word of prayer once I get up here. So, I'll start. Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to guide our steps today. Help us to make the most of the time and to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So, we go over a few different kind of random examples to perhaps get you to think some more about the concepts of things we're doing. So, example 1, suppose we want to consider all R, all right, such that the distance from R to, say, a point R1 is equal to the distance from R to another point R2. What would this be? Like, what's the set of all points that satisfy this equation? Like, what do those mean? What is the difference of two vectors? What is? Can we put this in words? Like, do we have a concept for what I'm looking at here? So, what we're looking at, this is the distance, right, from R to R1, right? And what's this? This is the distance, you know, from R to R2. So if I plot, say this is R1 and this over here is R2, right? And I'll just think about the endpoints, right? What's the collection of all points that is the same distance from R1 and from R2? What's that give you? Yeah?
A plane that's perpendicular to the line between them.
A plane that's perpendicular to the line. Can you tell me a point on that plane? How about if we draw the line from R1 to R2? What's the midpoint there? What would that midpoint be? How do we find the midpoint at 2 points? Do you guys know? That's something that's good to know. The midpoint, we take the sum of the points, right? And divide by 2. That gives us the midpoint, right? So like that point is equal distance. And it's easy enough to check that, right? If you plug in M into these formulas, you get the same vector up to a sign, right? So they're the same distance, this middle point is. And so I think Jacob's right. I think we get, so what were you going to say, Josh? Were you going to say the same, or?
No.
I mean, this is this blue thing here is a plane. It comes out at you, right? But if you think about it, right, there is any point here, right, R, we've got the same distance here, and over there. So this is just one of the end of chapter problems. I think it's worth just stopping to kind of appreciate what goes on here, right? What's the equation of this plane, this blue plane I just kind of half drew? Could you guys figure that out? What would the equation of the plane be? So if I draw it like this, here's the plane. We've got this point, let's say R2 up here, right? Midpoint's on the plane, and then R1's down here somewhere, right? How would you go about finding the equation of that plane? I mean, well, here it is right here, right? This is the equation of the plane. So you could just straight up square both sides and work out the formula from that, right? That's one way you could do it. But another way you could be more geometric, like what's the normal to this plane? Okay, in this picture, I could picture it like this, yeah? Over here, it would look like this, right? That would be a good choice for normal, right? We could use the normal is R2 minus the middle, minus the midpoint. That would give me a normal, right? Okay, so I wanted to give you an example where I don't actually give you specific points, but we have to kind of like reason geometrically. This is such an example. All right, so with this backdrop, what would it mean? Can you describe geometrically what the solution of this would be like? Okay, so now we're going to let, we'll let R equal to, let's say, xy now. Let's think about it two-dimensional for a second. All right, so what if I had R minus R1 plus R minus R2 equal to some fixed positive constant d, right? Number one. And what would, number two, what if we had the difference of this and that equal to a constant? What would that be? Do you guys know? What is that geometrically? What does it mean to have a collection of points where the sum of the distance between two fixed points is held constant? Do you guys know what that is? So one of the ways we can define an ellipse, right? An ellipse with two focal points, it's the collection of all points where the sum of the distances between the focal point and a point on the ellipse is held constant. So here the focal points would be R1 and R2, and like, if I was so foolish as to try to draw it, so like, if this is right here a point on the ellipse, then this distance here plus that distance there, let me draw it in red and green, right? That is, how long is that? Well, let me make it 2 markers long, okay? So I'll put the point out here. All right, here's a point on the ellipse. So if I'm, one marker, let's see here, so that distance, so I'm going 2 markers distance away, right? So right there would be another point on the ellipse, because the sum of the distances is still 2 markers long, all right? 2 markers long, another point over here, the sum of this distance, and so this distance, well, anyway, you have to, if I could do this correctly, we'd have an ellipse. But the key is that the distance from here, like this distance, say d2, and this distance d1, d1 plus d2 should be held constant d. That forms an ellipse. This is the vector equation of an ellipse in the plane. Distance from one focal point plus distance from another focal point held equal to a constant. Do you guys care to guess what number 2 is? If the difference between 2 focal points is held equal to a fixed constant, what do you think that is? What's that? So you could work this out. Actually, let's work this out. Let's pick a couple points and see if we can figure out what it is. So example 2, let me just pick a specific point. Let me say R1 is like, I don't know, 0, 2, and R2 is, let us say, actually, let me make it more interesting. Let me make it 1, 1, and I'll make this one minus 1, minus 1. There we go. And let us actually study what it looks like to say the distance from R minus R1 minus the distance from R minus R2 is equal to 1. Let's work out what this actually is. So here, we're looking at, the length of xy minus 1, 1 minus the length of xy minus 1, minus 1, right? All right, so what are we looking at? We're looking at the length of the x minus 1, y minus 1 vector minus the length of the x plus 1, y plus 1 vector. So, all right, that's what? Square root of what? X minus 1 squared plus y minus 1 squared minus the square root of x plus 1 squared plus y plus 1 squared equals to 1. Now that, at the moment, is not terribly familiar, at least to me. Can you guys see what it is? I mean, I can't, not yet anyway. How would we get rid of the square roots? What do you do? We should isolate the radical, right? Isolate the radical by putting it on one side and getting the other to the other side. And then what do we do? Natural enemy of the square. The radical is the square root, the square, so square both sides, like so. But when we square, we have to do the algebra, right? And so the algebra says that we have to have cross terms on the right-hand side. Of course, the left-hand side is just what I wrote, but the right-hand side, a little bit more interesting, because we get, 1 plus twice the square root of x plus 1 squared plus y plus 1 squared, right? Plus, well, x plus 1 squared plus y plus 1 squared, because the square root squared there gives you that. Now, if I FOIL this all out, I've got x squared minus 2x plus 1 plus y squared minus 2y plus 1 on the left-hand side. On the right-hand side, I've got 1 plus the radical of x plus 1 squared plus y plus 1 squared. And then, of course, that FOILs out to x squared plus 2x plus 1 plus y squared plus 2y plus 1. Did I miss my 2 times the radical? Oh, no. Well, all right. Well, let's fix that. But notice that there's a bunch of stuff that cancels, like this and that be canceling. We can cancel that one and that one. We got this y squared, cancels that y squared. We can isolate the radical once more, right? So we have twice the radical, x plus 1 squared plus y plus 1 squared. And what happens, looks like I've got a minus 4x minus 4y, you say? Okay. Do any of the ones survive? One of the ones survives. And it looks like I've got 1, 2, 3 here, and I've only got 2 over here, so there's a net minus 1, right? All right. So square both sides again. We get 4 times x plus 1 squared plus y plus 1 squared. What's that? I switcherooed it, to use a technical term. But I like what you're telling me. I'm going to put that minus over here and make these all pluses, because why have 3 minuses when we can just have 1, right? Okay, great. So 1 plus 4 times x plus y squared. Notice the parentheses. All right, so then that is 4 times x plus 1 squared plus y plus 1 squared. So that's a 1 plus 8 times x plus y plus 16 times x plus y quantity squared. So much suffering. All right. Rats, I'd hope this worked out nicer. Oh well. I'm reluctant to burn more class time on this one. I mean, we can FOIL it out and cancel some stuff, I suppose, but Fine. One more step. Yar. All right, well, I'm sorry. I have chose poorly. I mean, this means that we need a deeper magic to unfoil this thing. Can you tell me what this is, though, even though I can't prove it to you algebraically, but can you tell me what this is we're looking at? It's not an ellipse. This kind of thing, if you're looking at the difference of distances being held constant between two fixed focal points, this is a hyperbola. But this is a hyperbola which has focal points like 1, 1, and 1, minus 1, minus 1. I had hoped that this would work out to like y equals 1 over x, but oh well, that was wishful thinking on my part. Or I made an algebra mistake, but it's wishful thinking. Let's go with that. And so the difference in the distances is held equal to 1. So like, anyway, I'm not very good at visualizing the hyperbola in terms of like this direct picture, but I think, don't quote me on this, but I believe it's something like this, but I'm not 100% sure on that. So, anyway, my larger point to you is that there is a definition of hyperbola that's just in terms of the difference in distances between two fixed focal points being held equal to a constant. This defines hyperbola. All right, how about here's another example of this type, and then I'll stop with this stuff. But what if I had the distance from r minus, say, r naught equal to constant r? What would that be? And let's suppose r is x, y, z. What's this? So we're saying the set of all points equal distance from a fixed center point. What is that? A circle is kind of right. Depending on, but we have a z, right? So it's the sphere, right? Yeah. So like if we take a point here, r, and the center point, r, then r minus r naught is a radial vector to that sphere. All right. Okay, anyway, I wanted to play around with these kinds of calculations for a minute. Let me turn the page. Next kind of question. So here's a question for you. If A dot B is equal to A dot C, does B equals to C? What do you guys think? Not necessarily. What's your example? I'll give you an A. 1, 2, 3, right? So you could have what? You could have like B equals to, say, like what? 1, 0, 0, and C equals to, there are many choices, but how about like 0, 1/2, 0, right? Then we'd have A dot B equals to what? Is 1, which is also equal to A dot C, right? But B is clearly not equal to C. So can we cancel vectors off dot products? No. Not if we know a single dot product. How about cross products? What if you have A cross B? equals to A cross C. Is that enough information to imply that B equals C? Let's see here. How about maybe we could do something like 1, 1, 0 cross something equals to 1, 1, 0 cross something else. Maybe. I'm not sure if I can come up with a counterexample right off, but like I have to think about it for a second. But no, it's not enough information. Yeah.
Maybe 1, 1, 0 and minus 1, minus 1, 0.
What's your B? I mean, I'm saying this is A. So I just need a B and a C if this is A. So what'd you say? Minus what?
1, 1, 0 for B.
1, 1, 0 for B, and then minus 1.
Yeah, minus 1, minus 1, 0.
Minus 1, minus 1, 0. Ah. I think that'll do it, right? B is not equal to C, right? And yet, they're both equal to what? So apparently we can't cancel on the cross product either, right? Now, that example seems too easy, right? What if I told you that A cross B is equal to B cross C and they're both non-zero? Is that enough information? Well, I'll let you think about that. What about if we knew A dot B is equal to A dot C and we knew that A cross B was equal to A cross C? Would that be enough information to conclude that B is equal to C? Think about these questions. See if you can answer them. Now let me give you a slightly different presentation, set of questions. So like, how about this? What if instead of just knowing a specific choice of B and C, right? So here, the proper, more mathematical statement of this is there exists B and C such that this is true, right? Excuse me, there exists A, there exists A such that A dot B is equal to B dot C, right? There exists A. What if instead of there exists A, you knew for all A this is true? If I know, it's very different. If A dot B is equal to A dot C for all A, does B equal C? See, now the answer is yeah, definitely so. Why? How can you show that? How about this? If it's true for all A, what are the three most important vectors that we can think about? We can choose A equals to what? We can use X hat, we can use Y hat, we can use Z hat, right? So we have like X hat dot A dot B is equal to X hat dot C, and we have Y hat dot B is equal to Y hat dot C, and we have Z hat dot B is equal to Z hat dot B dot C rather. But what is that? What do these three equations tell us? This tells us that the X component of B is equal to the X component of C, right? And the Y component of B is equal to the Y component of C, and the Z component of B is equal to the Z component of C, which is to say that B and C have the same X, Y, and Z components, so they're equal, right? So if we know that the dot product of A with B and A with C, if they're matching for all possible B and C, well, yeah, that's definitely enough, yeah.
What if A was a zero vector?
Well, that's also true. It's still true. 0 is equal to 0.
Yeah, then B wouldn't necessarily have to be equal to C.
Yeah, but I'm not saying it's just true for the zero vector. I'm saying that A dot B is equal to A dot C for all A. The difference is here, if, to be more pedantic here, there exists A such that, you know. Now, if there exists an A such that's true, then that's not enough. But if it's true for all A, yeah, that's definitely enough. Yes, sir.
Is A like a vector function? Is that kind of, or is it just?
I'm just saying A is a arbitrary vector. So it's not a given function. So we're back to the start of the course again. I mean, we're not looking at functions of time just yet. Okay, that's another thing. But actually, I don't even need this to be true for all A, do I? If you look at what I just argued, what would suffice? If you know the dot products of B and C are matching for what? It's enough for them to match for x hat, for y hat, and for z hat, right? That's totally enough to get them matching, right? Anyway, you guys got questions? You can ask me questions. Otherwise, I will go on with these kinds of musings. See, to finish this question, I need Math 221. And I need Math 221 from about 6 weeks from now. So, my apologies. I was hoping that when I picked these two focal points, it just worked out to like y equals 1 over x, xy equals to 1. See, if this simplified down to xy equals to 1, that's actually a hyperbola which has the coordinate axes as its asymptotes, but I was not so fortunate. So anyway. Phew, what a mess. So do you guys have any particular questions? I got time for questions today, of course. But I do have more things to think about if you don't have really a question. Okay, well. Yeah.
Could you give an example, like from mission 1, where it's picking like a point on a plane closest to two other points?
A point on a plane.
It was like 1C or something, probably 2C.
Let's see here. So example, I guess this was example 3, wasn't it? I suppose this was example 3. This was example 4. So let me see if I can come up with an example of the sort of type you're talking about. Here, like you've got some, so you're given some line on the plane, and you've got a point off that line. What's the question exactly?
I can find the exact question. I think it's actually a line, not a plane. I was thinking of.
Well, tell you, well, you find that. Let me work a different example for a second here. Suppose this point is 1, 2, 3. And suppose that this line has parameterization r of t is equal to 4, 4, 4 plus t times 1, 0, 1. All right? That's a parameterization of the line. My question then is, what's the equation of the plane? Can you guys tell me how to do that? Yes?
You could take t equals 0, t equals 1, and 1, 2, 3.
T equals 0, t equals 1, and 1, 2, 3. So what do you mean? T equals 0 would give me a point here like that. So like r of 0 is what? Apparently 4, 4, 4, right? Great. And so I think what you're getting at is I can use that point to 1, 2, 3 to get me a vector in the plane, right? Well, I mean, it depends what you're after. I wanted the Cartesian equation of the plane, right? So I could make this vector A, right? A would be what? It doesn't really matter. We can go from 1, 2, 3 to 4, 4, 4 if you'd prefer. That way we'd have a positive vector, but fine. Minus 3, minus 2, minus 1 in my current picture, right? What's the direction vector of the line and how should I picture it? You can look at this, right? The direction vector is by inspection this. This is the velocity, actually, of that path, right? So V is like this, and I don't need to do further calculation. I can tell you already it's 1, 0, 1. So yes, we could have also done what Jacob was suggesting, which is to look at R of 1, and then probably you're thinking R of 1 minus R of 0 would give me that vector V. But I don't even need to do that, see, because I can already see V directly from this if you want. But what are you saying was good? I mean, that's not also not there's like dozens of ways to work this problem, all right? So the point is I've got A and I've got V, right? So what's the normal? How do we find the normal? We take the cross product. So the normal is the cross product of either A with V or V with A. It doesn't really matter. Which one do you guys want to put first? A. All right. So minus 3, minus 2, minus 1. Cartesian product. Listen to me. Cartesian product. Cross product with 1, 0, 1. That is 1, minus 1, plus 3, I think, 0, plus 2. If I haven't made some silly mistake, that should be 1, 2, 2. This is a cross product, so, oh, that's definitely wrong, right? So which one, where did I make my mistake?
The x should be -2.
This is -2? All right. Well, then the dot product with V is definitely 0. And the dot product with A gives me 6 minus 4 minus 2. That's 0. We're good. So yeah, I'm taking the dot product of N with my A and the V and checking. All right. So you can use the determinant thing if you want. It's your business. I only ask one thing, which is you check your answer and get it right. All right. So I prefer to do dot product. I prefer to do cross product in my head and use the formula I wrote down on the board. So that's what I do. You can do something else if you want. Anyway, so there's our normal vector. We got normal minus 2, 2, 2. And what's the base point? I mean, you got tons of choices, right? You could use 4, 4, 4. You could use 1, 2, 3. What do you guys want to do? 4, 4, 4? Base point. 4, 4, 4. All right, great. So minus 2 times x minus 4 plus 2 times x minus 4. Golly. X? Really? No. What goes there? Y. Plus 2 times z minus 4 equal to 0. There you go. Equation of plane. Now, of course, we could clean that up, right? Maybe a better way to write the answer is minus 2x plus 2y plus 2z is equal to, minus 8 plus 8 plus 8, which of course is 8, which then gives me, minus x plus y plus z is equal to apparently 4. I kind of like that as an answer more so. But they're both legit answers for the equation of the plane. Yes, sir.
The
I don't know, I just checked it worked. So, I mean, this dot that is 6, minus 4, minus 2, 6 minus 6 is 0. I think that's right. So, again, how you do the formula is your business, but I check my work, and if it's right, it's right. So, yeah, there's the, can you guys give me the parameterization of the plane? Can you parameterize this plane? What would a parameterization be? R of st, what could we do? We're going to use base point 444? All right, cool. Plus s times what? How about s times v? T times a, which was -3, -2, -1, right? This is a parameterization of the plane, since we know that 1, 0, 1 and -3, -2, -1 are perpendicular to the normal vector. That means that they must be tangent to the plane, and adding the 444 at the start puts us on the plane. So that is a parameterization of the plane. Of course, we could find 3 points and use the 3-point parameterization formula if you wanted, but there's a way. Yeah.
Does it matter which parameter you pair with which parameter? For S and T?
It's just a choice. Yeah, I mean, if I want to make it more fussy, I could ask you to, like, if you wanted to find a parameterization of just like a parallelogram on the plane, then it becomes more fussy, right? Like if I want to just parameterize the parallelogram like this, right? Then I'm to get from here to here, I have to let my t range from wait a minute, s. Yeah, from here to here, I let t range, I think. Oh, rats, I can't think. It's messing with me because the t in this parameterization is not the same as the t along the black curve, all right? That's fine. T can do double duty. But yeah, so as t, if we look at r of 0, 1, we're here. R of 0, 1 is at 1, 2, 3. And like r of 1, 0 is up here at like, that point, which we never found, but it's 5, 4, 5. And then this point over here is like, whatever that is, when I put in r of 1, 1. So if you wanted to parameterize the parallelogram, then you'd have to limit the domain to just like 0 to 1 for the formula we wrote, for both s and t. Yeah. Other questions? Let's do something else. I don't know, your question was about distance from a line?
You're given a point P, and it's asking you to find the distance from that point P to the line through 2 other points that are given.
Okay. So I think that's a good problem to use our projection and orthogonal projection concept on, right? So the way before I forget, the way tomorrow works, the start of class, you turn in your mission, right? I will not take mission 2 at the end of class. It must be given at the start of class. Then you work on the math battle, all right, which is an in-class group quiz. You guys work together and see what you can do. It will be some problems that are, routine, and there hopefully will be a couple problems that are much more, challenging. So hopefully I'll think of something. Is there anything you guys don't understand? Tell me now. Nobody's going to tell me what they don't understand?
So when we're given like a question where it was like you put up the distance plus the distance equals a constant, to figure out what it is, like if we didn't have like a graphing tool to figure out like, oh, that's going to be an ellipse, are you ever going to have a question where it's a different formula?
Oh, the reason for that discussion, I just wanted to draw your attention to the fact that we can define ellipse and hyperbola geometrically without actual use of Cartesian formulas.
Okay.
So, because I don't think that's something you maybe ever have heard before. So I think it's good for you to hear that, right? In terms of like how that actually works out for a given problem, well, there's a myriad of ways, I suppose. But your question is we'll pick 2 points. So we'll pick, let's say 1, 1, 1. I like 1, 1, 1. That's a nice point. And over here, 6, 8, 9, right? And we take some other point down here, whatever it is. Let's say 3, 0, minus 4. We should do some minuses. Then the question that we're asking, there's a bunch of different questions we could ask with 3 points, right? Find the equation of the plane with the 3 points, we could do that, right? But the question we're asking at the moment is what point on the line which connects these two, right? Which point here is, find the closest point, right? So like, I should give these things some labels so we don't have to write them. I'm going to call this P, I'm going to call this Q, and I'm going to call this guy down here R. So find the closest point on PQ, right, to R. Let's give a name for that point. What do you guys want to call it? We'll call that point, I don't know. What do you guys want? Let's use J. I haven't used J for anything. We'll call that point J. So, so I've drawn the point as if it's the the closest point. But if we take an arbitrary point, well, I think geometrically it should be evident that we want that to be a perpendicular bisector, right? Like, how do I find that point? Well, the way I usually do it, and there are various ways, is I think about this vector here. Let's call that A, right? And then I think about this vector up here, say B, which would be the PQ vector, right? And I can reach that point J, right, if I follow the, I want to find the shadow basically of A onto B, right? So I'm looking for the projection. Now there's a couple different questions to ask here. They're related, but they're different. The one question is how far is the point from the line segment? The other question is what is the point that's closest? Those are different questions. But this vector right here, right, would be projection in the B direction of A. Right? So from this picture I can see that J is equal to my starting point P plus that projection of A onto B. Now, if this is really a perpendicular bisector, I also know what the dotted line is too, right? That's what? Well, that's the, you're giving me the mechanics of it, but we have a name for that, right? The orth, right? Yeah, this should be orth B A, right? And that, now you're right, the formula for that is, what is it? It's A minus the projection onto B of A. That's true. Right, so let's work this stuff out. So first of all, I'll work out the projection. Remember the projection of B into the A direction, we can use the formula A dot B divided by, well, it's A dot B hat, that picks off the B component, and we put it in the B hat direction. Now, a nice formula for that is just A dot B divided by B dot B. And we multiply by B. Like this, we can calculate it that way. I guess I need to write down the vectors A and B, right? What are those? How do I get A? I do R minus P, right? And my B vector is what? It's PQ, right? It's Q minus P. So specifically, that is what? 2 minus 1 minus 5. And the B vector is 5, 7, 8. All right, cool. Now, so A dot B is what? It is 10 minus 7 minus 40 divided by B dot B, which is 25 plus 49 plus 64. That all gets multiplied by 5, 7, 8. Now that minus 37 divided by 138, you say? Okay, I'll believe it. Okay, so the closest point then, the closest point, J, apparently, is going to be 1, 1, 1 minus 37 over 138 times 5, 7, 8, all right? And we just have to do the math to combine those, right? So I would suggest getting a calculator and adding fractions, you know. Let me not burn class time on that since you guys know how to do that, right? That would give you the closest point. How do we find the distance then? The distance from the point to the line is defined to be the distance to the closest point, right? Distance to line should be the length of orth B of A, right? Which would be the length of what? A is, what was it? 2 minus 1 minus 5, and then I have to subtract the projection, which is the same as adding 37 over 138 times this thing. All right? So about 3 minutes of calculator work later, I would have the answer, right? These are not answers yet. This would, if if this is a problem, I would want these things simplified. I wouldn't like this as the final answer, right? I mean, I would give significant partial credit for this, don't get me wrong, but we should know how to like simplify these things, right? And to do that, you just have to add components and all that. Yes? No? All right. Let me ask you guys another question. So it's example 6, I guess, for today. Example 7. Y squared plus z squared equals to 1. Intersects the x plus 2y minus z equals to 10 plane. Parametrized curve. How would you do it? You do what? Say again?
Y and Z with cosine.
So you're seeing There's no sine and cosine in these formulas. Where are you seeing that from? I mean, she's right. But that took a creative leap, right, to see sine and cosine here. But I totally agree. We should put y equals to, what would you say, cosine t? And z equals to sine t. Now, you might say, oh, no, no, no. I want to make y sine t. I want to make z cosine t. Would that be right? Sure. You could make it like tons of choices, all right? These are just a choice. But these will give you y squared plus z squared is equal to 1, which is great, right? But, oh yeah, then to get z, but I also want, x plus 2y minus z to be cosine t minus twice sine t plus minus z is equal to 10. So my parametric equation for z, lo and behold, is, cos t minus 2 sine t minus 10. And so here you go, my parameterization. It's a package deal. It's, oh man, what's wrong with me? Oh man. Sadness. Yes, so sorry. Thank you guys. X. So I had them flipped too. Goodness gracious. So important comment. Don't just assume things work. Actually think through them so you don't do what I just did. Of course, I did that on purpose, right? For your learning. You're welcome. But x is equal to 2 cos t minus, plus sine t plus 10 as it happens.
Wouldn't it be plus 2 cosine?
All right. Now that we've got that out of my system. See? You guys are learning. That's good. There's your x. I mean, come on. Could you have done this 3 weeks ago? I mean, well, yeah, probably, but there must be someone here who now can do this who couldn't have done it 2 weeks ago, right? There must be at least one person. That person here exists. If you're a person who doesn't yet know what's going on, that's okay, but it starts to not be okay next Tuesday. So you need to figure out what we're doing. Like, it's not much. We are parameterizing what we can and then dealing with the more complicated part by just plugging in those formulas into the other defining things, right? Like, so both of these are surfaces, right? Y squared plus z squared is a circle, is a cylinder, right? It's a cylinder on the x-axis. This other thing, x plus 2y minus z is equal to 10 is some kind of, I don't know, some kind of plane. All right? And those are intersecting on some curve, and probably comes back around. I don't know. Don't ask me for the full story, but there you go. That's the full story. And we just need to do 0 less than t less than or 2 pi, and there you go. We have parameterized the curve. That make sense? Yes, sir.
Will we lose points if we didn't put the bounds?
Depends on the question. But I do want the bounds usually. But, it kind of depends on the question. It's best practice to give the bounds, but also at the same time, the choice of bounds is not unique because of the ambiguity of the way the question was asked. Right? So like parameterize the curve of intersection. And then if I added further language, cover it just once. All right, then 0 to 2 pi would be fine. But you know what? So would 2 pi to 4 pi. Or minus pi to pi. Same story. Different choice of parameter, right? I wanted to go through a more physics calculation with you for a second here. Let's suppose that we have particle going in a circle. So we can say r of t is, let us suppose, r cosine theta, r sine theta, all right, where theta is function of time t, all right? So I'm being a little bit cagey here. I'm just telling you that we know it's going in a circle, but we don't really know how fast it's going in a circle. Exactly. It depends on theta, which is a function of time, right? And so we could pick different, thank you. We could pick different, So here's the question is, can we describe what the velocity and the acceleration is for this thing? Let's work it out. So like the velocity, right? dr dt is what? We've got, minus r sine theta d theta dt. Very good. We have to do the chain rule. R cosine theta d theta dt, right? And so lo and behold, we can rewrite this thing as r times d theta dt, right? Times minus sine theta. And let me make this three-dimensional just for kicks. Now, okay, fine. To be fussy, the speed is what? It's r times the absolute value of d theta dt. You see, because if d theta dt is positive, then you guys are right. If d theta dt is negative, that means that the vector that I partitioned off, factored out here, this is either plus or minus t, right? So the plus, if d theta dt is greater than 0, the minus, if d theta dt is less than 0, all right? Because either the circles, either the path is going, as we get to this point, right? It's either going this way at that point, right? Or it's going that way. So d theta dt greater than 0, d theta dt less than 0, right? Clockwise is negative in the theta direction, yeah? Okay, so great, there's the velocity. If you like, we can assume that, do you guys want to assume d theta dt is positive just to keep things simpler going forward? So let's assume d theta dt is positive for the sake of the rest of this discussion, then the speed is in fact r theta dot. Yeah, you can do that. Theta dot is d theta dt. All right. And the velocity in this case is just r theta dot times the unit tangent. And what happens when we differentiate again? dv dt, right? And what's that? Well, that's, now we got to differentiate, r d theta dt times this minus sine theta cosine theta business, right? And what's required there is a product rule, right? Because theta is a function of time, and d theta dt is a function of time, right? So we differentiate this, we get r d squared theta dt squared times minus sine theta cosine theta 0, and then plus r d theta dt times what? Times like minus cosine theta d theta dt, right? Sine theta